I want to talk today about, I'm not, as James indicated, I'm not going to tell you how to solve complex problems and actually solve them and so on. I'm going to rather sketch things about the overall problem that makes it very hard, and I'm going to go into detail in a few places where in particular I think the way we've been doing things is wrong, and then sketch alternative ways of approaching that I'm involved in. Sustainability is a problem that automatically is a problem in complex systems because it sits at the nexus of so many different fields. If we're going to understand sustainability, we have to understand problems like climate, so we need better theory, better measurements, improved computational power, the ability of weather and climate models to make good answers depends on things like how good are the computers they're running on in a very sensitive way. We have to understand critical questions in economics to understand something like what it's going to cost us to mitigate greenhouse gas. How are we going to reduce inequality, which is something that comes up sort of naturally in sustainability as well. How much should the present generation sacrifice for future generations? I'm going to actually discuss that question in some detail, actually trying to overthrow some of the central dogma that's been cast about on that question. If we want to plan sensibly for something like global warming, we have to understand technological progress. How are technologies going to improve over the next 100 years? Which technologies are good bets? Which technologies are not? How should we deploy our money in order to get the solutions that we need to solve the problems we need to solve? There's, of course, a host of problems in geology, in ecology, in space science, understanding demographics and population control, security, energy. I'm not going to touch on most of those. Let me just say that all of these problems are strongly overlapping with each other, and it's hard to discuss one without the other. I didn't even realize I have a whole other slide there. Danger of armed conflict, political questions, sociology, how do we educate people and convince them to act? And to be honest, if you take a problem like global warming, I think that's the biggest challenge at this point, because I think scientifically we know how to solve the other problems. At least we know the basic lines of attack that will solve them. What we really don't know how to do is get people mobilized when we're dealing with a problem that will take 100 years to play out. And once we get there, it's going to be much harder to get out of than it would be if we acted now, because the Earth is essentially acting as an integrator, an accumulator of greenhouse gases. It's very hard for people to think about systems with those kind of properties, and it's very hard to achieve the kind of social willpower that we need to confront these things. Any kind of decision making in this area is inevitably confronted with basic things about human beliefs, about what is fair, who should win and who should lose, and how much do different groups have to sacrifice. And at the end of the day, we always have to remember, at least as scientists, I would argue our goal is to help people understand the relation between actions and consequences and cause and effect, and not to tell people what they should do. We can say, well, if we do this, this is what we think will happen. If we do this instead, something different will happen. That's our role as scientists. I may have a personal opinion about which future I prefer, but I think one needs to try and separate those things. Now, the Earth is a complex system, and we need to manage it as such. So I want to begin by just saying a little bit about what complex systems are, although given what I've been hearing about the amazing program here in complex systems, this is the PhD program I wish I had gone through when I was a kid. I don't want to bring coals to Newcastle, so let me just say a few things. So, complex systems are systems with many interacting parts that display emergent phenomena such that the system exhibits different behaviors or exhibits behaviors that are qualitatively different than those of the individual components, and in which the whole can be greater than or less than the sum of its part. It's the discipline of complex systems, I would say, is motivated by belief in two principles. One is that complex behaviors emerge from interactions at a lower level. And the other is that there's similarities between examples of complex systems that merit studying them side by side. And there's, I would say, a strong versus weak version of complex systems. The weak version is that, well, we'll gain some insights. We don't need to specify too much, but it's useful to at least juxtapose different disciplines and phenomena in different areas of science to understand their similarities. The strong version would say that, well, someday we might actually have a theory from which all these things could descend, so that, say, social evolution and biological evolution might actually have a common starting point. And I think we're seeing a few glimmers of that in current research, but we're a long way from it. And some people will argue that the strong version is never going to happen, not even close. Now, I ultimately think complex systems is important for engineering principles. As I said, the Earth's a complex system. We need to manage it that way, but we need to understand how do we manage complex systems, because engineering a complex system is different than, say, building a bridge, though a bridge may already be fairly complex. But complex systems are built from the bottom up, and I would argue engineering a complex systems is a bit like gardening. That is, you typically don't have full control over all the pieces. You know, you can build the internet, but you might not realize that what's the main use of the internet going to be? Spam, right? What is it? 80% of the messages that flow around the internet are spam. You have these emergent problems. You build the internet, the spam grows like crazy, as organismic things tend to do, and then you have to devote a lot of effort to somehow keeping it under control. So in complex systems, we can lay down the rules, we can observe the consequences, we can modify the rules, but you can't directly, oftentimes, influence the outcomes. As in gardening, you know, you prepare your plot, you put the seeds in the ground, you make sure they have enough water, you make sure the pests don't get them, or you try to, but ultimately it's the plants that have to grow. Now, precisely because the structure is emergent, it's inherently difficult to predict. Some of the properties may be robust. Some of them may be more robust than you want them to be because you'd like to get rid of them. Others may be very sensitive to the details and very path dependent. So there's a challenge to sort those things out and figuring out what is what. Now, to illustrate some of the challenges in complex systems, I'm going to begin with a simple identity that sometimes just goes under the abbreviation of IPAT. And what this stands for, can I move around? The camera can deal with this. Is IPAT means impact equals population times affluence times technology. So in other words, the impact of what we do on the Earth has to do with, first of all, how many of us are there? What's our level of affluence? In this case, if our level of affluence involves automobiles and large houses, we're likely to have more impact than if we live in a forest around a fire and don't have those things. And then times technology. Technology here means maybe not quite what you would think. Really, it's how much impact are we having per unit of affluence. So we could be living in our nice house with our car and having a lot of impact because we're mining fossil fuels to support all that, or we could be living in a completely self-sufficient house on a solar-powered vehicle and having relatively a lot less impact. So this technology then is the technological efficiency in providing affluence with lower impact. So the basic outline of at least the next portion of the talk is that I'm going to go through each of these bullets and make remarks about these bullets and maybe try and point out some aspects of this that are not completely obvious. So first of all, let's talk about population. Well, world population. This is an estimate of world population that over the last 2,000 years. And I've begun just by plotting things in a normal linear scale so we can see the world population rising, staying very low for a long time, and then rising amazingly rapidly to the present. You can see we're kicking out from the first billion here to 6 billion there. This plot's already a bit out of date. I think the dot's now up here somewhere. So population, as we all know, has grown enormously. People often talk about this as Malthusian growth, but Malthus actually postulated that population should grow exponentially. Is that what's happened? No. Actually, I'm now plotting the same thing on semi-log scale. So I've just changed the scaling of the y-axis here. And what we see is if I plot things on semi-log scale and population is growing exponentially, we should see a straight line. We still don't see a straight line, though. We see something that's upwardly inflecting. In other words, population has grown faster than exponential. Malthus was, in some sense, an optimist. Now, what's actually happened has been super-exponential. And so to see how that works, you can imagine, let's say x is the population. So the derivative of population grows as some constant times the population. If we were talking about exponential growth, we would just solve this equation. The solution to this equation, this differential equation, is an exponential function. But if it's growing super exponentially, it must be growing at something faster than that. So we must have an exponent that's greater than 1, say some value beta that's a positive number. And when we solve an equation like this, we get a solution that looks like this. That is, we have a constant times some critical time in the future. And you can see this if you like to do calculus. You just integrate this equation. Some critical time in the future minus the present time raised to the minus 1 over beta power. Now, if you look at this solution, what you will see is that if t equals tc, this is 0. So the fact that this is a negative exponent means we have 1 over 0, and population goes to infinity. So there are some other less natural ways to get super exponential growth, but this is the most natural one. Now, if we indeed fit the data that I was just showing you to that equation, what we see is if we take 2050 as a rough critical time, we see a much closer approximation to a straight line, suggesting that in fact that's roughly the model that we've been following for a long time, 2,000 years. Now, this was first noted by the first people to take a careful look at this data were actually some electrical engineers, and they published an article in Science on November 4th, 1960, and they actually managed to get this title, Doomsday, Friday the 13th, November 80, 2026. So they had TC, the critical date, equals 2026. This is back in 1960. It's somewhat sensitive to exactly where you're putting this. And they pointed out in this article, which has a sort of pleasant by modern standards joking tone, that if their prediction is right, people won't die from starvation. They'll die by literally being smashed to death, because once the population starts growing that fast, things accelerate at an unbelievable rate. Now, they realized when they said that they were being tongue-in-cheek, because this just plain can't happen, right? It's physically not allowed. So what this is saying, though, is that I think is interesting, is that the Earth has to break out of the pattern that it's been in for at least the last 2,000 years in this century. We simply cannot have population go on growing at the rate that it's been growing. And in fact, if you look at the data since about 1950, there's been a very noticeable downturn that has to do with the fact that as societies become increasingly affluent, birth rate tends to go down. It depends on things like education of women. So lots of things are happening to stabilize the population, but the point I want to make is that just from this analysis, you can see that we have to get off the track that we have been on. There's simply no choice. Now, there's also something interesting that comes out of this, that is, how could Malthus have been wrong? How could we have a population that actually grew at a super exponential rate? The only way that happens, and let me go to this slide here, is that technology has been improving. That is, if technology were fixed, we'd be like bacteria growing in a petri dish. You put some bacteria in the dish, population initially grows exponentially, And then at some point, the dish starts to fill up, population growth tapers off, and you go to some asymptotic growth rate. That is, there's an S-curve associated with population growth in any fixed resource environment. But people have been different than that because we've had improving technology. In particular, our ability to grow food has improved dramatically since Roman times. And there's theories about that, most of which, or many of which, are predicated on the idea that as the population grows, your ability to invent things grows, which means that you accelerate the rate of innovation, which allows the population growth rate to grow. There's a theory by Paul Romer that's more or less along those lines. My collaborators, Jane McNerney and Francesco Caravelli, and I are actually working an alternative that maybe I'll get a chance to say a little bit about at the end of my talk. Now, I guess I already explored the punchline. I already articulated this punchline, so let me just keep moving on and now talk about affluence. Well, what about affluence as measured, say, by per capita gross domestic product? Well, this is a data set put together by Brad DeLong showing the growth of per capita GDP through time, and as you can see, it looks pretty similar to what we saw before. In fact, we plotted on semi-log scale. We see a similar issue, that the curve inflects upward. We plotted in the way that I plotted before, where we plot it in log-log, assuming a power relationship with the same critical time. We see something that's at least plausibly a straight line, although with some fairly serious wiggles. So again, it seems that per capita GDP has grown super exponentially. Now let me say there's a debate about this because some might argue that it's just a persistent trend. Others would argue that what happened here is the Industrial Revolution. And so you were growing at one rate up until then, and you started growing at a completely different rate after that. Well, I think we don't know what the story of that is in detail. Now, one of the questions that always comes up when you talk about affluence is whether, if we're going to be in a sustainable world where the impact staying constant, even once population levels off, how are we going to become sustainable vis-a-vis the Earth? Are we going to voluntarily give up affluence? Or are we going to change what we mean by affluence? And I tend to think the latter. I think these changes will somewhat be forced on us, but I think it's already worth noting that if you even look at what GDP means, that's changed substantially through time. GDP is increasingly about small things that do lots of informational tasks that put less loading on the Earth than the things we used to make. In fact, there is much discussion about the dematerialization of the economy. So while the economy is still very much a material thing, we still consume enormous amounts of resources for each unit of affluence, we are actually historically consuming less through time. But once again, as we can see from looking at this curve of affluence, where there is at least some evidence for a finite time singularity, we see the same kind of pattern that we're going to have to break out of the pattern of ever-increasing affluence that we've now been on for a long time. Now I'm going to move on to the next part and say something about technology. One of the biggest questions in confronting climate change is the question of what will it cost? And what is the appropriate action that we should take now to spare future generations? How much cost should we bear? How much cost should future generations bear? There's a whole field that's emerged in economics of integrated assessment models that attempt to give answers to these questions. Let me just say that I'm quite skeptical about the answers these models produce. They assume equilibrium, they assume full employment, they don't deal with things like economic stimulus, they don't have any instabilities in them, there's no uncertainty in economic growth that comes out in any really plausible way. They only consider technologies that already exist. They assume exponential discounting. They aren't back-tested against real data. I think this is a critical point. We're talking about making bets that are going to influence, in a dramatic way, the world that our grandchildren live in, based on models that are not properly tested against real data. So I'm now going to make comments about a few parts of this. I first want to make an analogy to World War II. And imagine Roosevelt, say in 1941, when America was considering entering the war. Actually, Roosevelt knew for a long time we were going to end up in the war. He was just trying to figure out how to make it politically feasible. It's worth recalling that in the United States, between 1939 and 1941, baseball got more coverage in the newspaper than the war in Europe, even though you guys were on the verge of being wiped out at that point. So Roosevelt was very much aware, on the other hand, very much trying to bring popular opinion around. And so he was, he did call his advisors in and say, what is this going to cost us? And they toted up. Well, we've got to build this many tanks. We've got to build this many planes. They looked at the cost of tanks, the cost of planes. The bill looked enormous. He, of course, was going to do it whatever it cost. But what did it really cost in the end? That is, with hindsight, what answers should they have given him? And I think none of them would ever have predicted the real cost, because what I'm now showing you here is the US per capita GDP in real terms from 1860 to fairly recently. And I'm once again plotting this on semi-logarithmic scale, so I'm plotting the log of GDP against time. And we're now looking at the GDP year by year, and I've drawn a trend line in that roughly provides the best fit to this data. Now, in the US, we had the Great Depression, which started about here and reached its trough in the mid-30s. And at its worst point, the depression in the United States was actually worse than it was in Britain. We had 25% unemployment, much like Greece right now. The output of American factories was a fraction what it had been before. Now, the war started in Europe, and despite the fact that maybe people were still spending a lot of time reading about baseball, the factories started to churn because, Winston Churchill, actually I don't know if he could call Roosevelt at the time, but he made it very clear what Britain needed to survive, and Roosevelt did everything he could to get the US producing ships, tanks, airplanes, all the things that Britain needed to win the war. And so we went from this point here, this data point I think is 1939 or 38, and we go rocketing up till we actually overshoot the original trend line by the time the US pulled out of the Depression. We went from a point where unemployment was at 25%, where virtually everybody was employed, and in fact, women were employed at a scale never seen before. So what did the war cost in the end? I'm actually eager to collect data to try and actually put numbers to this, but it clearly cost a hell of a lot less than people originally thought it would, because it stimulated the economy so strongly. And for Britain, in an area of trying to recover from the combination of a recession and austerity, I think this is a lesson that should be paid some attention to. And by the way, the models that we're using for climate mitigation don't take these effects into account. Now, I want to come to another point, which relates to the question of discounting the future. And I'm going to do this in some more detail because, first of all, it relates to my own work. And secondly, because I think it's a good lesson in how one has to be careful about received wisdom and questioning things that don't have good grounding in empirical data. When we think about something like global warming, as I said, it's a critical question to decide how much are we willing to spend now to help future generations. Now, the way an economist would standardly ask this question goes back to something that was done by Paul Samuelson, a paper published in 1937, where he showed that exponential discounting had certain nice properties of being stationary and time consistent, that he argued meant that it is the appropriate way to discount the future. And 99.9% of economic papers that have to confront this problem are based on exponential discounting. What it means is that the value of something in the future is equal to some discounting function times its present value. So if we use exponential discounting, then we take the present value of something and we multiply it by a factor of the form e to the minus rt, where t is the time into the future and r is the rate of discounting, in order to assess its future value. And just to see the justification for this, if I say to you, well, would you rather have $1 now or $1 a year from now? Well, okay, how many people want the dollar now? A year from now? Okay. Well, obviously, you know, if nothing else, you can take the dollar now, put it in the bank, and then you'll have $1 and, you know, at current interest rates, $1 and a pence, right? But you will have more money probably in the future. So this is one of the arguments one can use to justify, one of many arguments, or I should say one of several arguments one can use to justify discounting the future. Now, a central problem is that under discounting, exponential discounting, and at a reasonable rate, the far future isn't worth very much. For example, if you take a discount rate of 6% after 100 years, the discount factor is 0.0025. So that means that $1 now, or let's say $400 now, is worth $1 100 years from now. So economists have argued that we're then making a serious and irrational sacrifice if we spend a lot of money now to confront global warming, that is to deal with something 100 years from now, when the discount factors are this large. So for instance, there's something called the Copenhagen Consensus, included 4 Nobel Prize winners in economics, and they've issued statements saying more or less what I just said. And this is a statement from the website concerning global warming. If we use a large discount rate, they, meaning the effects of global warming, will be judged to be small effects. Criticizing a study that only used a discount rate of 1.5%. So actually the point that just raised is how much discounting you do is very sensitive to the discount rate you use. If you use a 10% discounting factor, at 10%, the discount factor in 100 years in the future is 5 times 10 to the minus 5. At 5%, it's 7 times 10 to the minus 3. At 1%, it's just 0.37. So there's a world of difference between what you choose to discount. And in fact, the whole decision-making process, to a significant extent, pivots around this single question. So we're going to now investigate this in more detail. You might ask, well, what does data have to say about this? How do people actually discount things? Well, a lot of studies have been done on that, and it turns out that people don't use exponential discounting. In fact, what happens is the effective discount rate decreases through time, and people who do experiments where they give people trade-offs, like the one I gave you about do you want $1 now versus $1 a year from now, if you take that data and you fit functional forms to the data, it's better fit by power law functional forms like the one I'm writing here. That is, rather than an exponential in time, we have 1 plus a constant times time raised to some power. This is often called hyperbolic discounting because if this power is 1, we have the equation of a hyperbola. And so this is, when this was first realized, this was viewed as a major puzzle by economists and has been widely regarded as evidence that people are simply irrational. If they were rational, they would discount exponentially, but because they're irrational, they use hyperbolic discounting. Now it turns out that in fact, you can do these experiments on animals. Pigeons are smarter than you think, and you can train a pigeon so the pigeon realizes I can pull this lever and get a pellet now, or I can pull the other lever and I'll get 2 pellets in half an hour. And so they train these pigeons to do this. They give them a wide variety of time scales. Same thing. They exhibit pretty much the same discounting behavior that people do. Now, sorry, this slide's a little bit technical, but doesn't really matter. I'll just go over it. If you don't get it, that's okay. as I said, Paul Samuelson, the reason economists like exponential discounting is because it's time consistent. That is, if you ask what utility do you get at some point in the future versus utility now, it's if we discount we satisfy an equation such that the utility we get from consuming something now is discounted. It's a discounted version, the utility in the future is a discounted version of the utility in the present. And it's also stationary in the sense that we don't have to change the discounting function as we go along. So that's why economists have liked this. Now, with John Giannakopoulos, I've actually shown that once you're in once you're in an uncertain world where rewards are uncertain, hazards are uncertain, economic growth is uncertain, interest rates are uncertain, and if these uncertainties are correlated in time, then actually Weitzman already pointed out that the certainty equivalent discounting function is no longer exponential. These uncertainties modify that. But John and I showed that in fact, under uncertainty, exponentially discounting is not time consistent and instead something else is. So in other words, the rational behavior is no longer exponential discounting. And we worked out a specific example of this called the geometric random walk, where we assume that if interest rates, to focus on the opportunity cost problem I mentioned a while ago of, you could put your money in your bank now, in the bank now, but the part that you guys actually might have wanted to consider is the question of whether we're in a deep recession or not. Because if you're in a deep recession, it could actually be quite a bad idea to put your money in a bank, because you might actually have less a year later than you would have now. And in fact, if in a geometric random walk, what we assume is interest rates are uncertain, say because of inflation, so that if we have an interest rate now, at each step the interest rate can either go up or it can go down. And so we go to the next time step, and from there it can either go up and go down. So the interest rate, but we're actually talking now, I should say, about, well, the interest rate can either at this extreme go to zero, and I should say it's a geometric random walk, so we're really talking about the behavior of the logarithm, or it could drift off to infinity, but it's uncertain. Now the geometric random walk is actually a model that's widely used in Wall Street and to price bonds. One can then ask, if you think about the discounting problem by, say, imagining a benefit in the future, like this is what it's going to cost to deal with global warming 100 years from now, and you move it back along all of these interest rate paths, along paths where the interest rate is very low, there's very little discounting. Along paths where the interest rate is very high, there's a lot of discounting going on backwards. The paths where the interest rate are low dominate, and that's why the effective interest rate goes down with time, because these paths get a much bigger weight than those paths. And in fact, when we do simulations on this, we see that, and once again, I'm now plotting things on log-log scale. We look at the discount function that we have as a function of time. If we had exponential discounting, we would be on this path right here. And you can see that over short spans of time, we stay reasonably close to that with a geometric random walk. But over longer spans of time, we end up with a discounting function that's decaying much more slowly. And in fact, as you can see by the fact that this is a straight line on log-log scale, is actually decaying as a power law. That is just like hyperbolic discounting. So we get hyperbolic discounting back, not from saying people are just irrational and they do this for some funny behavioral reason. It's because this is what people in pigeons should do if they're properly taking into account uncertainty and the fact that those uncertainties are correlated in time. Now, so we're able to prove actually in the paper we wrote that in fact this discounting function is always asymptotically going as 1 over the square root of time. And let me just comment that this actually makes a big difference because the exponential function is integrable. In other words, if I ask, what's the integrated benefit that I'm going to get under exponential discounting, it's going to zero fast enough that I can integrate it to infinity and I'll get some finite result. But if I integrate this function here, the integral of this function to infinity is infinite, which would say that we ought to put an infinite weight on the far future. So a dramatically different answer. Okay. Now, let me just say, again, I apologize for the equation here, but I think I can explain the idea pretty well. Actually, with some Spanish collaborators, Jaume Mas Oliver, Josep Perello, and M. Torralbo, we are studying more realistic models. So we've actually gone out, we've said, look, what is the right interest rate model if we want to think about long-term questions like this? And I'll just show you some data. We have a data set here that goes back to 1689, if I'm remembering right, for the United Kingdom, and back to about 1820 for the United States. And in this plot, you see in red the nominal interest rate for a 10-year bond, nominal meaning in the currency value, in real currency value, or I mean actual currency value, versus what we see here is inflation. So you see inflation bouncing up and down, the nominal interest rate bouncing up and down. Whenever the inflation rate goes over the nominal interest rate, that means that money is actually shrinking. That's the time when you don't want to put your money in the bank because you're going to actually have less than you did before. And what you can see is in both cases, well, they're not common. There are many periods where you see interest rates or inflation running sufficiently out of control that you end up with periods where you have where you actually have negative real interest rates. So that was a somewhat surprising feature to us. We now asked what model for interest rates can we find to fit that? Well, the model that we have, the best model we found so far is what's called an Ornstein-Uhlenbeck process, where just to read this so you see how it works, because it's not as complicated as it looks, the change in the interest rate is equal to minus some positive constant times the difference between the current interest rate and its more or less average or centering value that it's attracted to, plus some kick times some random noise. So that's the way the model works. In other words, if you go back and look at these data series, it's saying there's some kind of level that things tend toward, they oscillate around that level, and they can, crucially, they can go negative. Now, when we actually analyze this model, what we see is we see even more radically different results from the exponential, simple exponential model that we saw before. Depending on the parameters, you can see situations where you start out with one exponential rate and then you asymptotically converge to another much slower interest rate. You can see situations where you start out with exponential decrease in the discounting function and then it just approaches a constant. And maybe even more surprising, it could go down and then it can actually go back up so that the discounting is exponentially increasing in time. Now, how is that happening? Well, it turns out when you think about, actually let me go forward a couple of slides. If you think about, okay, I have a slow slide here. All right. If you think about what we're actually doing, and I think I'm just going to skip this, going back on these paths, if you actually have negative interest rates, they make huge contributions when you're going back in time. So even if there aren't very many of these paths, they completely dominate everything and overwhelm what's going on. So if you have enough volatility in the economy, you can end up having that be the dominant process. So I'm sorry, I've got a recalcitrant slide here. And in fact, we analyze long data sets on 14 different countries, and we characterize their behavior. This line here corresponds to the dividing line between, on this side, things asymptotically decrease exponentially. On this side, they asymptotically increase exponentially. If they're sitting on the line, they're more or less asymptotically constant. And what you see is basically there's two types of economies. The ones that essentially sit right very close to this line, and the ones that are out here in the exponentially blowing up zone. Most of the main economies like the UK and the US are on this line, but some of them actually that you wouldn't think would be too bad, like Australia and Denmark, are out in this zone. All of the countries that had runaway inflations are out in that zone. Here's a zoom in just to see the countries that are actually around the line. So what's the takeaway message from this? That based on current evidence from an actual analysis of historical interest rates, economic growth is too uncertain to justify high levels of discounting. So in other words, the future is worth a lot more than people have been saying it is. Arguments that say, well, you know, we don't even know what technologies we'll have in the future. The economy is going to grow so much. We ought to just work on other things like inequality or malaria and let global warming happen, and then we'll just fix it 50 years from now, are not justified when you think about uncertainty. And I think it's worth noting that in the Depression, as I already showed you, the US economy actually shrank for 15 years. And from the fall of Rome to the Renaissance, it took the Italians almost 1,000 years to get back where they were when Rome fell. My favorite remark on this comes from the Iroquois Constitution, one of the Indian tribes that inhabited North America when the first Europeans arrived. They have something in their constitution called the Great Law of Peace. They say in every deliberation we must consider the impact on the seventh generation, even if it requires having skin as thick as the bark of a tree, of a pine. Okay, I want to say a little bit about technological progress. Okay, that's about right. As I mentioned, one of the key questions is whether or not technological progress is predictable. Now, you might think that technology ought to be completely unpredictable. After all, it depends on innovation, and innovation, the very name implies a kind of unpredictability. But with collaborators, Bela Nagy and Quan Bui and Jessica Tranchik, we assembled a database on technologies, and we asked, well, can we predict how technologies improve? So we used cost as a measure of technology performance, and we also had data on production, and we did experiments where we would sit in 1980 and we'd say, can we predict what happens in 1990? And the answer was, well, actually, we can make pretty good predictions. They're not, of course, perfectly accurate, but they're a lot better than nothing. They get worse, as you would expect, as you try and predict further forward in time. And we tried several competing hypotheses, such as one we call Wright's Law, which has been around for a long time, since 1936, that technology costs drop as a power law of cumulative production at a rate such that every time you double cumulative production of a given technology, and Wright, by the way, first noticed this for airplanes because he was involved in airplane manufacture, every time you double production, the cost, he noted, would drop by 20%. So it means costs drop at a decreasing rate in terms of number of the cost drop per airplane, but in a fairly predictable way. Everybody, I'm sure, is familiar with Moore's Law, which was initially a statement about density of transistors on semiconductors, but it's sort of morphed into a statement about processor speed, and it actually works very well also as a statement about cost, although actually Wright's Law works even better than Moore's Law for cost of computers. Now, so we've been looking just to say empirically how well can we predict things, and we've demonstrated by using historical data that we can make pretty good predictions. And actually, before I show you this slide, I want to show you another slide, and I'll come back to that one. And let me just state a hypothesis. So far, we've seen three types of energy. If we think about, say, energy generation, we've got technologies where the price tends to drop as production increases, like solar and wind, and I'll show you an example in a minute. And then we've got things that depend on fossil fuels, which to first approximation obey a random walk with zero drift, and at least when you look at historical data. And then you've got some puzzles like nuclear power, which, despite the fact that nuclear power is undeniably a sophisticated technology, for reasons that are not well understood, has not gone down in cost. And so let me actually show you a plot, first of all, just to motivate this. So here we're plotting energy costs since 1860, and with an extrapolation going all the way to 2050. So we've got cost in this axis. I'm measuring I'm measuring this based in dollars per kilowatt hour. of electricity. So in other words, if this is 0.05, that means it costs 5 US cents per kilowatt hour of electricity generated. And so this black line here shows the amount that the equivalent in cents per kilowatt hour for coal. In other words, if you took an existing coal plant, suppose that existing coal plant existed back in 1860 and was making electricity, and you look at the price of coal, what would that have translated into in terms of electricity cost from that coal? I could have showed you a much more complicated plot with prices of plants and stuff. This is the most striking thing. So I would say the main thing that we see from this is that the price of coal over the 150-year period we look here wiggles, but roughly speaking, it stayed relatively constant. It's fluctuating within a few cents. In fact, if you fit a model to this, what you see is it fits a random walk with zero drift, flat. In contrast, what about solar photovoltaic energy? Now for that I'm going to use a different scale, but I'm going to suggestively line it up with the other scale. And so the natural units to measure this in are price in dollars per watt peak, because of course the effectiveness of a solar cell depends on things like, is it here in England where, as I now know with all too much visceral certainty, the weather is miserable. I've endured a winter here now. I grew up in New Mexico and I can tell you that's hard, versus say in the Sahara Desert. And so, but nonetheless, you can look at how much does it cost to take a module with to produce a module with fixed characteristics. And I'm showing you here this since 1976. So you can see that during that period it's dropped by a factor of about 50. And furthermore, this is Moore's law. We're plotting this once again on semi-log scale. We see solar photovoltaic prices dropping at roughly an exponential rate of about 3.5% per year in a fairly steady way. In fact, I could have extended this back. There's kind of a slope break, but if you look at the whole curve, it's a factor of 3,000 since 1957. Now, so we have two contrasting things. We have this technology-like behavior that is common to many of the other technologies we have in our database, where costs drop steadily, versus commodity, coal, where costs vary but don't drop. Nuclear power is a puzzle. Here I show little red triangles for US nuclear reactors during the history of the US nuclear reactor program. The cost of electricity as a function of the date when the nuclear reactor came online. And what you can see is that it's a kind of a cloud, but the overall trend has been that the price has gone up. Now, you have to bear in mind that, of course, our concept about safety for nuclear power changed. So, because there were 3 Mile Island and Chernobyl happened during this period. And so people got a lot more safety conscious, the plants were delayed, the costs went up. So there's certainly a factor of that in here. Nonetheless, even if you normalize for that, at best the cost held even, subtracting for that. So there's a pretty dramatic difference. And let me just point out that if you believe this trend, then, and you extrapolate it forward to the future, by 2050, solar PV will actually be cheaper than coal. And let me just note what this line here is. The Department of Energy in the US has something called the Sunshot program that had a target of bringing photovoltaic modules down to 50 cents per watt peak, where they said things should begin to be competitive with coal. Now, it's a bit of a complicated story because, of course, there's also the system cost of installing it. That hasn't come down as much. One can quibble about whether I've lined these things up right. I'm just sort of taking their target and using it here. But I think regardless of it, you can see there's a big difference in the pattern, and one needs to think about these dynamics in planning for the future. And let me just say in this plot that we've looked at forecasts where we actually can construct error bars. So here we're looking at the price of a photovoltaic unit. This is the DOE Sunshot target. We're extrapolating forward in time under sort of current conditions with the error bars here in red, versus if there was a program that would subsidize in a much more massive way production of solar PV, then we argue we should be roughly on this path here, and we can go through and analyze that kind of cost. So I'm just about to wrap up. Now let me return to this question about, is economic growth sustainable? US production GDP has grown on average at about 3% per year for 150 years. Can that be sustainable? Well, no. But is there something, what could be sustainable? I don't think what's sustainable, on the other hand, is as pessimistic as saying the economy can't grow at all. Why? Because, as I already mentioned, if you look at the environmental impact per unit of GDP, it's been shrinking. I don't have as good a number on that, but it's at the order of 1%. So if it is indeed 1%, then it's saying we should be able to grow at 1%. And under this identity, if the population's holding constant, our affluence can increase at a rate of 1% per year, providing our technology gets more efficient enough such that it's dropping at 1% a year and compensating. Though one can argue to even get back to the point where we're sustainable, we actually have to make a reduction in the impact number from where we are now. I want to just wrap up. I guess I already said this, really, that as scientists, our duty is to understand cause-effect relations and understand the effect of taking actions. As citizens, our duty is to create a world consistent with our values where we'd want our grandchildren and great-grandchildren to live. I think we have to always be clear about which of those. And I think one of the lessons I've learned in entering this field is that one has to be very skeptical of received wisdom. We're talking about decisions that are really critical, and we shouldn't take anything at face value. That doesn't mean we can delay action as a result, but we shouldn't assume just because somebody important says it's true, it is. And I want to end by saying, you know, to follow up on my remark about complex systems engineering being like gardening, the world is our garden. I mean, it's estimated that human influence on the world we may be consuming as much as 40% of biomass that's being produced by fixing sunlight now. We're now dramatically interconnected. So though I grew up in a place, I grew up in a town of 5,000 people that was 50 miles to the next town with 5,000 people with a vast wilderness just north of it. And as a kid, I had visions of, that I can always go be in the wilderness and be by myself. But part of what we see is everything's connected now, and that wilderness is strongly connected to everything we do by things like CO2 accumulation and global warming. That wilderness may cease to exist, at least in its current form, if we don't take action. So I think we have to manage the environment and our economy like a garden, and keep that in mind all the time. So on that note, I'll end. Thanks.